So our project this semester was in partnership with GE Vernova. It was a water pipeline for a nuclear reactor cooling system. The goal of our project was to design a system that would run water through a pipeline to be used to cool down a nuclear reactor. And the system would also be cyber. This project was also cyber informed, so the system would be invulnerable to cyber attacks. The system used two kinds of sensors to check for leaks in the main line, a pressure sensor and a flow meter, and once a leak was detected, the water would switch to a secondary line. If the leak was also detected in the secondary line, then the pump would shut off and both of the valves would close. To prevent our system from being vulnerable to a cyber attack, we have one type of sensor outputting to the Mark V IE controller and the other outputting to a Raspberry Pi. These two devices are able to communicate with each other and tell the other when they detect a leak. Um, so if one is messed with, the other should still be working properly and is able to tell the first system that there's a problem. Our project goals and deliverables is that the system needs to be able to detect a leak in the pipes and shut off the system as needed. It needs to control flow rate based on these readings, and it needs to be secure from the outside environment and from cyber threats. We needed to have an emergency shutoff and have it be operational in case of environmental or cybersecurity issues. We also needed to have a joint demo with all GE groups and teams, where Team 1 would provide access control to the overall system, and Team 2 would create clean water that would be fed into our system as our input. Our system also needed to be able to determine if there had been a cyber attack if there's a discrepancy between the actual readings that we were getting from our sensors and the expected readings we got from the Raspberry Pi. And this is a picture of our project. Here at the bottom, you can see our pump leading to two lines. This is the main line with with our valve and two flow meters and two pressure sensors. This is our second line with one valve, two flow meters, and two pressure sensors, and then both of them have a leak, as seen here.
This is a block diagram of our system. It pulls water from the water treatment into a pump and then flows into the primary or secondary lines. Each line has a flow, pressure, and then faucet following with the pressure and then flow, which then is outputted into a tank and then looped back into the water treatment. Each faucet simulates a leak, and each flow and pressure transmitter is connected to Raspberry Pi, Mark 6E, and HMI. This is an overall hardware design view of our system. Uh, there is access control, which is group 1, water treatment, which is group 2, and then our system design. Um, a nuclear power plant with the cooling line can be an example of how important our system is. Without this, it would not be able to run a nuclear power plant safely and efficiently to power cities.
So here we have our software architecture. So the system begins in idle state until the operator starts the pump via the HMI. Once the flow begins in the primary path, there are multiple pressure sensors being pulled. And if the pressure is out of the expected range, then it'll close the primary side valve, open the secondary side valve, and log the event in the HMI. If the secondary line leaks, the system then just shuts off. It closes both valves and shuts off the pump. The HMI now also includes start-stop resets, changing thresholds, and there's a Raspberry Pi that calculates the pressure values using Bernoulli's equation and compares them to real readings to detect possible cyber attacks. And here's a flowchart of what I've just stated as well.
So this is what the main screen of our HMI looks like. On the top we have a system overall status visualization, so we can see that every component has its own indicators. We have three different states. Green means that the system's running and the component is open. Yellow means that the component is idle or closed, so basically not being used at the moment. And red means that there's an alarm active and that component is closed or is not working at the moment. We also have an e-stop button, which basically kills the power and shuts down the entire system. And also we have the text up on the top which says no alarms active. In case of an alarm, it turns red and it starts blinking. In the bottom we have the alarm viewer, which basically gives you information about the alarms that are active or that were previously active, and on the right side we have our pressure readings for all our four pressure sensors. And this is the manual control screen for our HMI. On the left side we have manual overrides. The two-way switch gives us the ability to switch between auto mode and manual mode. Once you switch to manual mode, you can manually control the components of our system. So for instance, the switches that say main valve and secondary valve allow you to turn the valves on and off, and then the switch that says pump allows you to turn the pump on and off. And then you can hit reset, which basically puts the system in its previous status or state, and then you can switch to auto mode and the system will run on its own. On the right side, we have our threshold control, which allows us to change or modify the thresholds that we use to determine if the pressure is too high or too low and trigger an alarm based on the situation.
Here for the hardware methodology, our system will remain at rest until water is pumped through it. There are pressure sensors and flow meters throughout the system so that when a leak is simulated, it will be able to tell and then thus send a message to the HMI and the controller to fix the issue by opening and closing valves. And if both sections are leaking, then the valves will be shut and the pump will be shut off. And once the water is stopped or rerouted and the leak is fixed, the valves are then reopened by the user. And our system is supposed to collect clean water from Team 2, who's doing a water purification system.
For the software methodology, the system remains idle until the operator requests to start the pump. At any point, the operator can press the stop pump button, which serves as a kill switch to immediately halt the system. While the system is active, it continuously monitors pressure sensor readings. If the pressure deviates from the expected range, the system will close the valve to the primary pathway to contain the issue, and it notifies the operator through the HMI with a clear alert that includes a diagnosis of a potential leak. The system then opens a valve to redirect water to the secondary pathway. Pressure continues to be monitored to ensure there's not an additional leak. If a second leak is detected, the system responds by immediately closing the valve to the secondary pathway and shutting off the pump to prevent further issues. Once the leak is resolved and the system is restored, the operator can restart the process. The valve to the primary pathway is reopened, the valve to the secondary pathway is shut, and the pressure will continue to be monitored. To enhance reliability and security, we'll also implement a digital twin in Python. The digital twin will simulate the physical behavior of the system using Bernoulli's equation to model expected pressure and flow. By comparing the simulated data to the real-time sensor readings, the system can detect discrepancies and report any of those as a cyber attack on hardware devices.
For the cybersecurity aspect of our project, our main goal was to protect against false pressure readings. This was to make sure that someone didn't force the pressure high or communicate with our sensors in a way that would compromise our system so that we'd have a leak but the pressure was reading normal. To do this, we implemented flow sensors that were connected to the Raspberry Pi rather than the controller, and then we connected these two devices together via Ethernet and then utilized Modbus TCP to allow these to communicate with each other and send system information, pressure readings back and forth. To do this, we used Bernoulli's equation to calculate expected pressures based on our flow rate. So this is a physics concept, basically says that these things should be equal on either side of the equation, and everything in here is constant except for the pressure and velocity, which is calculated as the flow rate. So we took our pressure readings in real time and then compared them with our flow rate readings in real time to make sure that the pressure readings were what they should be based on the math of the other pressure sensor. So if one of the pressures downstream was forced high, but there was no flow there, then this physics equation would tell us that there has been a compromise to our system because the pressure is not what it should be based on the equation.
And here's our demonstration video.
So we're going to start off from the panel here to the HMI screen. We'll start by running the reset command, and you'll see it's going to zero our thresholds here. And then it's going to set them automatically based on ambient pressure right now. And the idea is these limits for each of our main and secondary sides, those are going to determine where pressure can drop below. If it drops below these limits, that's when we'll start to get errors. And then I'll start running the pump here. The pump is on. Right now we're running from our tank through the main side and back to the same tank, so it's a kind of circular system there. After 10 seconds, the pressure will stabilize, and then we'll be detecting errors. So if you open our simulated leak faucet, hear that click, that was us switching to our secondary side now. And that's because the pressure dropped at the far point when we simulated a leak. And now if we simulate a leak on the secondary side as well, you should hear the system will shut off just like that. System into manual mode. And now I can open and close each valve manually. Whenever I want. We have a safety feature. If you close both valves, the pump auto shuts off because you don't want to be running the pump down no open pipe. But if I open one valve, the pump will turn on. This is in our current running state, and this is just saying that we're running down the main pipe, and that our secondary pipe's in idle state. If we go ahead and throw that first leak, you should see the main side should have an error. There we go. Indicated by the red meaning the valve's closed, red here meaning that pipe's in error. But now this is green and this is green instead of yellow. This means it's gone from idle to active. This means we're running down the secondary side. And then if we throw the secondary leak, the pump should stop, and you'll see both sides are red, as well as the pump icon here is also red. So we're gonna start running the pump down our main valve. And I'm gonna go into our software here and go into our pressure comparison. And I'm gonna set our pressure here to be at constant 34, which is above our threshold. And so when that happens, if we pan over here and we simulate the leak, the software cannot detect it. So this is like we're in a cyber attack state. And in this situation, we have our Raspberry Pi here that is checking with Bernoulli's equation, and it will shut off, you just heard that, the system. And so even in the case of a cyber attack, we do have protection against that as well.
In testing, our system performed according to design expectations and safety requirements. We first introduced a simulated leak into the main pipeline. The controller correctly detected the pressure drop, automatically closed the leaking valve, and successfully rerouted water through the secondary line. Next, we simulated a second leak in the redundant line. As designed, the system reorganized the failure and executed a full shutdown, closing all valves and turning off the pump to prevent further loss or damage. In parallel, we established a Modbus TCP connection between the Bronx 60 controller and Raspberry Pi, which allowed us to cross-check live pressure sensor values between the control system and our digital model. The Raspberry Pi ran a Python-based digital twin using Bernoulli's equation to compute expected pressure values. During testing, this model reported discrepancies that aligned with our injective fault, effectively simulating a potential cyber attack scenario. Meanwhile, the HMI operated smoothly, displaying real-time sensor data and allowing user interaction for system control and monitoring. Overall, the entire leak detection and response sequence followed our intended logic, demonstrating both functional reliability and cyber awareness in a simulated nuclear cooling pipeline environment.
For this project, we would like to thank the Holcomb Department of Electrical and Computer Engineering and the Design Essentials Lab. We would also like to thank GE Vernova, especially Mr. Lester Childs, Mr. Jeremy McCune, Mr. Reese Taylor, and Mr. Rodney Stowe. We would also like to thank Dr. Lou Yu, Mr. David Moline, Ms. Gail Black, Ms. Alyssa M. Konoreski, and Ms. Jeanette Hendricks, as well as Dr. Hassan Radza and GE Team 1 and Team 2. Thank you.